Okay, we are now going to make a longish digression into graphs. But graphs we would not make a combinatorial view or computer science algorithmic view, but as topological objects. Okay. So firstly, to clarify, I am allowing both loops. So this is a loop and multi-edge. There can be two edges. So you'd all have seen graphs, but there's a bit of a difference in terminology in these two respects by what we mean by graphs. Okay, so that said, let's try to formalize this. Now again, there's more than one way of formalizing it, but I'll use the way which is the most useful for topology, low dimensional topology, topological methods and group theory and so on, which is a graph is going to be determined by a set of vertices and edges. Okay, so this is given by, well, let's see. So first of all, we're going to have V a set of vertices. E is also going to be a set, but it's not going to be just the set of edges as you see them. So here you see 1, 2, 3 and 4 edges, but E is going to have 8 edges for this graph. Namely, I'll think each edge as being one edge oriented this way and one edge oriented this way. So each edge is really going to be viewed as a pair of edges. Okay, so this means, so it has a width, a fixed point free involution. We won't give this a name, instead we'll have some notation for it. It's going to be E mapping to E bar. Okay, so I'll have to clarify terms. So E bar, the term involution means E bar bar is E itself, and fixed point free means that E is not E bar. Okay, so an edge is not the same as itself with the reversed orientation, and you reverse orientation twice, you get this. And of course, crucially, you should have a relation between these two, which is you have an initial point map which maps edges to vertices. So this is, we'll call it initial point. Now we don't need formally to have a separate terminal point map, so we define a map from tau from E to V by, of course, the terminal point of an edge is the initial point of the same edge reversed. Okay, so we have an initial point and a terminal problem. So this gives you a combinatorial object. So given all this, this is a finite data in terms of sets. It need not be finite. It will usually be what we call locally finite. So for that we'll need this soon. So let me just define the term link of V in the graph gamma is the set of all edges E in E such that the initial point of the edge is going to be equal to E. Okay. We'll see examples. So in this case, so this is an interesting example. So suppose I took this as V1, V0. Well, what is the link of V0? Well, it actually has 3 edges. The one that goes out this way, the one that goes up this way, and the one that goes down this way. Because this loop has initial and terminal vertex this point. So whichever orientation you take, the initial vertex is this point. And this is a trivalent vertex. Okay, so the valence of the vertex is indeed the size of the link. That's one of the nice features we get by modeling it in this way. Okay, so this is an example to keep in mind. So similarly, these all have link which is 3 as well. So for topology, naturally we don't just want combinatorial objects like that. We want a space here. So we want to define mod of gamma, which is mod of gamma of, not f of gamma of EV. Of course, it also depends on the rest of the data, is given by, well, it's going to be a quotient space. Mod gamma is going to be V. I'll take this as discrete topology, the vertices. I'll take the disjoint union with something that depends on each edge. Okay, so let's look at each edge in E. So it could be simply written as E cross 0, 1. Okay, again here E is discrete, but crucially the whole thing divided by an equivalence relation. Okay, so for each vertex we take a point, for each edge we take an interval. This is what you would expect. Okay, and with tilde is the equivalence relation generated by the following. So you have to take the symmetric transitive closure of these. All of these are pretty obvious. So if I take a vertex in, well, I don't know, but if I take an edge in E, okay, and then if I look at a point in the edge, ES, so S is going to be in 0, 1. So this is going to be a point in E cross 0, 1. Well, it's equivalent to a point in the flipped edge, but which is the mirror point. Okay. And also, of course, the initial point in this edge, so for all E in edge this is true, and for all E in edge this is true, E comma 0 is equivalent to the point which is the initial vertex of V. So now, sorry, not of V, of course, initial point of E. This is in E cross 0, 1, and this initial thing is a vertex. So these are in the two different components. So vertices are glued to the initial points, and of course, so it follows also that E comma 1 is identified with the terminal point of E for all E. This follows by the two axioms with E bar, so you don't need this as a separate assumption. So this is what will give you a space corresponding to this. Okay, and then of course in the whole thing we have a quotient topology. Okay. So let's look at this topology a little more effectively. So here let me take a little graph. I have this edge, I have a loop, maybe I have a bit of a tree-like structure here. This goes on, and then it closes with a triangle, and just for fun we have another guy. Okay, and what are the basic neighborhoods? For E in E, we look at any open interval. Here is going to be a basic neighborhood. That's clear because its inverse image is going to be in the space of which you take the quotient is just going to be the same interval in the edge oriented this way, and the corresponding interval when it's oriented the other way as well. So this is more formally for E and E, and if I look at AB as an interval in 0, 1, you look at E cross a single point cross AB. But how about vertices? They are more interesting. So let's pick an example with a loop, because that's a little more subtle. So what is the link of this guy? Remember, the link of this guy consists of an edge which goes this way. It goes all the way around. This edge, which is the same edge but going the other way, same edge in the final quotient, and an edge that goes this way. Okay, all these have initial vertices. And then suppose I take a little interval here, half open interval, and half open interval, then their inverse image is going to be open, as long as we also include the vertex, and this is what we shall specify. Yeah, so let's formalize this a little bit. We can express it in the following way. That is for V in V, and so we specify a function, let's call it epsilon, which will map the link of V, the set of all edges, to, let's just say, 0, half. You could even take 0, 1. So it's going to be a positive number, and it's within half to avoid collisions. It doesn't matter because we need a basic neighborhood. So let's keep this clean, and we define, let's define a neighborhood of this. Let's call it U epsilon and V as going to be the set V union. So it's the image of this. So it's the image. So I should say be the image in the quotient. So even here, this is actually the image in the quotient. So this is the image of V union, the union over all edges in the link of V of the interval from 0. So to stick to my convention, I have to say E I can even write it as a set, the set of pairs E comma S, where the E is already in this link, and so I'm looking at 0 is less than or equal to S is strictly less than epsilon of E. Okay, so I have to pick the sizes. Now this can give a funny topology if link is infinite. So you could have at a point infinitely many edges going out, and you could end up with smaller and smaller intervals. So this is not the usual product topology, which would mean intervals, and it's not the usual metric topology either. It's yet another topology that we have. Yeah, so we are looking at V union this set. Okay, so this could be peculiar in this context, but we'll usually assume locally finite, in which case any reasonable topology is going to be the same as any other topology. Mod link V is less than infinity for all V in V. And that's what will be the case with all our examples. Okay, so with this topology, let's look at an example, and we'll look at a familiar example, which is going to be, it's going to be S1. But let's look at what the graph is. So graph has vertex has just 1 point, V is just 1 point, let's call it 1 for example, and E is just 2 points. Okay, so we can call them E and E bar or something like that. Okay, and I of E is of course forced to be 1. Okay, my point is that with this kind of knowledge of the topology, we can see that the result is actually homeomorphic. So this is mod gamma, this is homeomorphic to S1. Namely, how would we define it? So you define a function on the quotient topology, define phi from mod gamma to S1 as the quotient of mapping phi of E comma S. This phi of E comma S is going to be E to the 2 pi is. Okay, and just for completeness, phi of E bar comma S is going to be E to the power of 2 pi I into 1 minus S, and phi of V is going to be equal to just 1. So this will give you V is 1 in this case. So this is equal to 1. The only vertex is 1. We called it 1. It was just a name, so it mapped it to phi of V equal to 1. And what we have to see is this is continuous. So one way it's continuous because of the universal property of quotient topology. That is, if you have a map on the upper space which is well defined on the quotient on mod gamma, so this is whatever it is by tilde, it's automatically continuous. But the other way, you want to show that this is a homeomorphism. So what you want to show is that this is an open map. And for that, you look at just basic open sets. If I take an basic open set here, its image is going to be an interval here. Okay, so that is fine. And if I take a basic open set here, it is a little interval here which may be asymmetric. Maybe this side is different from this side. But nevertheless, you can see that the image here is an open set. Okay, so you can see that the images of basic open sets are open sets, from which you can deduce this is an open map, that it's a bijection is elementary just by reversing these functions, and hence we see that this familiar space S1 is the same thing as the topological space associated to this combinatorial object. Okay, this example was done just because once we should be clear about what this is. Okay. Next, we'll turn to morphisms between these spaces and their relations to coverings, which will make things very nice to work with later.